Ever feel like GPU prices are just made up? Like some invisible hand is just spinning a wheel to decide if that RTX 4070 is 500 or 800 today? What if I told you that we could build a price lie detector using the same math NASA uses to track satellites? No crypto bro guessing, no FOMO, just pure regression. Today we're going to build a model that looks at 20 different specs, from VRAM to clock speed, and tell you exactly what a card should cost. And the best part, we're going to use AI to find out which fancy features are actually just marketing fluff designed to overcharge you. By the end of this video, you won't just be a PC builder, you'll be a machine learning strategist. We're diving into the core of classical regression in machine learning. You're going to master simple linear regression, where we will find the golden line between specs and price, multicollinearity, by spotting when two specs are basically telling the same story and confusing your AI, Lasso and ridge regularization, the no-nonsense filters that penalize useless data to give you a clean, accurate prediction. Let's stop guessing and start calculating. Think of a GPU like a car. If I tell you a car has a huge engine, you expect a high price. That's simple linear regression. One cause, one effect. But a GPU is a mess of variables. You have VRAM, clock speed, power draw, and RGB lighting. This is multiple regression. Now here's the trap. If I tell you a car has high horsepower and a fast top speed, I'm basically saying the same thing twice. In AI, we call that multicollinearity. It's like two people screaming the same answer at you. It doesn't make you smarter. It just gives you a headache. We'll show you how to fix that with a tool called StandardScaler. Okay, before we train any model, we have to get our data into a form that AI can reason about fairly. Right now, our GPU specs are on totally different scales. VRAM goes up about 24, clock speeds are in the thousands, and RGB scores bounce all over the place. Let's head over to VS Code and see it in action. Alright, before we run this, let's quickly walk through what we're actually doing. First, we load our dataset. This is just a table of GPU specs and their market prices. Then we split the data into two parts. X, which contains the features we'll use to make predictions. In our case, VRAM, clock speed, power draw, and RGB score. And Y, which is the thing we're trying to predict, the market price. So think of X as the evidence and Y as the answer. Then comes the important part, StandardScaler. This tool transforms each feature so that its average becomes 0 and its spread becomes consistent across features. In other words, we're converting everything into the same standardized measurement scale before the regression model sees it. And notice something important. We're only scaling X and not Y. We don't scale the price here because we want our final predictions to stay in real dollar values. Now let's run it and see what that transformation looks like. Alright, this might look messy at first, but this is exactly what we want. Each number you're seeing now represents how far that feature is from the average, measured in standard deviations. So for example, look at the very first row. That means the VRAM is about 1.98 standard deviations above average. The clock speed is 1.55 above average. The TDP is 2.13 above average, and the RGB score is basically average, slightly below. Notice something important. Everything now lives in roughly the same range, mostly between -3 and +3. That's not random. That's what StandardScaler does. It centers every feature around 0 and scales the spread so they're comparable. So now when our regression model starts learning, it isn't biased by raw units like thousands of megahertz versus 8 gigs. It's comparing everything in standardized units, deviations from the average. And that becomes especially important once we introduce Lasso regularization, because Lasso penalizes coefficients based on size. If features weren't scaled, that penalty would be uneven and misleading. So this step isn't flashy, but it's foundational. We've just made the dataset mathematically fair. Before we train, we need to see if any features are twins. That might confuse the model. We'll use a correlation heatmap to spot multicollinearity. Let's try that out. Alright, Before we run this, let's unpack what we're doing here. We're creating a correlation heat map, which is just a visual way of seeing how much two features move together. If two features are highly correlated, it's like they're saying the same thing in slightly different words. For example, if VRAM and memory bus speed always increase together, our model might get confused. It doesn't need both to understand the impact on price. This is called multicollinearity. The heat map uses colors to make these relationships obvious. Dark red means a very strong positive correlation. Dark blue means a strong negative correlation. Lighter colors mean little or no correlation. So when we run this, pay attention to any features that are almost identical. Those are the ones we might consider dropping later to keep the model simple and stable. Let's run the code. Look at this heat map. We're looking for the danger zones, those dark red squares with the score near 1. See the 0.95 between VRAM and TDP? That means they move in lockstep. In regression, the AI tries to assign a specific price weight to every spec. But when two specs are twins, the math can't decide which one is responsible for the price. It's like two people trying to steer the same car at the same time. The model loses its mind and gives you wild, inaccurate predictions. But now, look at the safe zones, the low points. See that 0.02 between clock speed and RGB score? That's near zero correlation. They are total strangers. In the world of AI, this is actually gold. It means these two features are providing completely unique independent information to the model. Our goal is to find features that correlate with the price, but not with each other. By spotting these twins early, we can drop the redundant spec, keep the unique ones, and ensure our price detector is both stable and sharp. Now, the marketing fluff filter, Lasso regularization. This is the magic that saves you money by identifying useless features. Let's see the code. Okay, now we're getting to the fun part, the marketing fluff filter. Lasso regularization is like a strict parent for our model. It looks at all the features and says, do you really contribute to predicting price? If not, goodbye. The key here is the alpha parameter. Think of it as the strictness level. A higher alpha is stricter, meaning more features will be zeroed out if they don't really matter. A lower alpha is more forgiving and lets more features stay in the game. So when we run this code, we'll train the Lasso model on our scaled features and then check the coefficients. Basically a score for how important each feature is. Anything near zero, that's the fluff. It's not driving the price, even if marketing wants you to think it does. Later, we'll see exactly which features are truly influencing the GPU price and which ones are just there to make the spec sheet look impressive. This is where AI saves you money by ignoring the distractions. Let's run the code. Here's what this means. These numbers are the contribution of each feature to the GPU price. VRAM has a huge coefficient, about 400. That tells us that memory size is the biggest driver of price. Every extra gigabyte really moves the needle. TDP and clock speed also matter, but less than VRAM. Coefficients around 50 to 59. That's still meaningful, but smaller compared to VRAM. Now check out RGB score. It's only 0.67. That's tiny compared to the others. In other words, RGB lighting barely affects price at all. Marketing hype? Yep, that's what it is. You can imagine each coefficient as a weight. VRAM is carrying the heavy bag. TDP and clock speed are moderate, and RGB barely lifting a feather. That's why we called it the marketing fluff filter. Lasso literally tells us which features are fluff and which actually matter. Here's another important takeaway. The scale of the coefficient also reflects how Lasso sees importance relative to other features. Features with near zero coefficients are essentially ignored by the model. They aren't hurting predictions, but they also aren't helping. So if you were deciding whether to pay extra for RGB lighting, the model just gave you the answer. Don't. Focus your money on VRAM, clock speed, and efficient power usage. That's what actually drives the price. Now let's step back and see the big picture. This is where all the pieces, scaling, correlation checking, and Lasso come together. By using multiple regression, our model learned which specs actually drive GPU prices. The output told us that VRAM is the heavyweight, followed by TDP and clock speed, while RGB lighting barely moves the needle. That means the true value of a card isn't its flashy marketing features. It's the memory and power efficiency that matter. Because we checked for multicollinearity earlier, we also avoided redundancy. For example, if we had both model year and architecture generation in the dataset, the model might get confused, but now we only include one, keeping the predictions clean and stable. Here's the fun part. Once we feed a card's specs into this model, it gives a fair price. Let's say our AI predicts a card should cost $450 based on its actual specs, but Newegg, a brand, lists it for $650. That's $200 we can avoid wasting, just by understanding which features truly drive value. This is the real power of regularization and smart regression. It filters out marketing fluff, accounts for redundant features, and grounds the model in reality. It turns guesswork into informed decisions. That's why this step is a game changer for PC builders and anyone who wants to shop smarter. Alright, here's the big takeaway. More features don't automatically make a better model. The right features do. If your data is messy, scale it with StandardScaler. If your features are redundant, check for multicollinearity. And if you want to cut out the fluff, let Lasso or L1 do the pruning for you. Remember, don't just build a PC, build a brain that understands the market. With this approach, you're not guessing prices, you're making informed decisions. Take this rule with you. Explore first, model second, always.